Hello everyone, welcome to the session. I'm Saptarshi Mukherjee. I currently work at Google as a software engineer 3 and I've been a computer programmer for quite a long time. So in this playlist we are discussing the problems, the ways to solve different problems that came in Codeforces round 922 div 2, and in this particular video I'll be discussing this particular problem C, that is XOR-distance. So as I mentioned in my first video where I basically illustrated and summarized about all the problems, this problem is based on bit manipulation, one of my all-time favorite topics. In topics of bit manipulation, you basically have to look at the bits, you have to visualize, and then there is that simple fiddling with the bits that we need to do in order to finally get the solution. So yeah, let's see how this can be solved. So you're given three integers, a, b, and r, and you have to figure this out. A XOR x minus b XOR x for x belonging in this range 0 to r. You have to find the smallest value. So you have to choose this x. You can choose any x that lies in this range. R is given. So the range is given. And you have to select an x such that this sum is the minimum possible. A and b are given. And now this sign means the absolute value, and that means the bitwise XOR. So how to solve this problem? The values are very large, a, b, and r. So let us try to understand through one or two examples what this means. So let's say a is equal to 9, b is equal to 6, r is equal to 10. So if a is equal to 9, that means we are basically asking that, hey, 9 XOR x minus 6 XOR x, what is the minimum value that I can get of this computation? So now let's try to understand this. What does this XOR do? What does this XOR do? So let's say x is equal to something like 4, or let's say something like 5. Now what will this XOR do? So that means we are saying 9 XOR 5 minus 6 XOR 5. So XOR basically works in this way. 9 XOR 5 means you have to write 9 and 5 both in binary form. 9's binary form is 1001 and 5's binary form is 0101. When you find the XOR, it basically becomes 1100. So 1 XOR 0 is 1. 1 XOR 0 is going to be 1. Then 0 XOR 1 is 1. Then 0 XOR 0 is going to be 0. And 1 XOR 1 is going to be 0. So this is how it works. And now we can say, okay, 6 XOR 5. 6 XOR 5 is basically 110 and 101, which basically gives us 011. The same XOR operation. This is how much is it in decimal? So it's 8 plus 4, which is 12. This is, I'm basically doing a binary to decimal conversion, and this is 3. So basically, if you calculate this thing, you will get it in the, if you compute it in your program, you will get it in the decimal form. So the decimal form will be 12 minus 3. These values you now have to put. So it's basically 12 minus 3, which is equal to 9. So here it is 9. What if I choose x equal to 0? If I choose x equal to 0, then that will mean 9 minus 6, which is equal to 3. Right, so we can choose anything. 9 XOR 0 is 9 and 6 XOR 0 is 6. So 9 minus 6, 3. So in this way we can choose anything. If we choose 5, then our answer is 9. If we choose 0, then our answer is 3. So if we choose some other x, then our answer will be something else. And this is what we need to figure out, that hey, what is the minimum possible? So I'm getting 3, I'm getting 9 in two different ways. What is the minimum possible? This is what we have to compute. This is the question. Now the problem arises, okay, how should I be able to solve it? In bit manipulation questions, since the entire intricacy is in the bits, is in the binary digits, so the solution also needs to be approached from the bits. At the individual bits, we need to make our logic. What should be our logic with these bits so that we get the best answer? The answers lie in the bits, and that is my favorite part in bit manipulation. So let us see. Let us see. First of all, a basic logic when you solve this kind of problems. When you have to minimize something, let's say minimize something a minus b, where a can be changed a bit, b can be changed a bit. What should be our strategy? If you have to change, if you have to minimize, let's say, instead of um, absolute sign, you have to minimize the a and a minus b. What should be your strategy? The strategy can be that bring down the a or bring up the b, right? The first one, bring it down, and the second one, bring it upwards. If you are given the question basically that minimize, there is a maximum number and there is a minimum value which will be lesser, or maybe it's something like this. There is something which is more and there is something which is less. So how do you basically minimize the difference? So you can say whatever is more, I will bring it a bit down. Whatever is less, I'll bring it a bit up so that they come closer, right? They come closer, the difference reduces. So if I have to minimize the difference of two values, I can say that the greater one should be reduced, the lesser one should be increased so that they somewhere come closer. Don't do something like this that the greater one becomes the lesser one and the lesser one becomes the greater one. The absolute value remains the same. The absolute difference remains the same. That's not what we are targeting. We rather want to bring them as close as possible. So when the question comes to something like this, let's see what we can do. Let's take that example itself. 1001 and 110. 1001 and 110. What can we do? Okay, should I change this particular bit? So this is 9 and this is 6. Should I change the first bit? First bit is defining who is greater. By changing that particular definition, we will end up reversing the entire thing. The greater one will become the lesser one might become the greater one. There is no point in doing that. So we can say, yes, let the greater one remain the greater. Let us define, okay, this will remain the greater. So no need to fiddle with it. No need to fiddle with it. Okay, if we want to change the next one, should we change this next one? If we say, okay, let's XOR the bit, let's XOR at this position. So if I say, okay, in my x at this point, if I have a 1, what happens? This 0 gets converted to 1 and this 1 will get converted to 0. If I XOR it with 1, the 1 will become 0 and the 0 will become 1. Will it help me in this case? No, because already this one is greater. Now in the greater one, if I again turn a 0 into a 1, I never want that, right? So in the greater element, let's say this is the greater element. This is this is a lesser element. This is some intermediate bit at this position. So if you see that you have something like this, if you have the top one is 0 and the bottom one is, the lesser one is 1. Obviously that is good. If you change it, if you want to toggle it, if you basically say, hey, I want to XOR with 1, I want to XOR at this bit, then this will become 1 and this will become 0. So the greater one will increase further, the lesser one will decrease further. You don't want that. You can see the lesser one will decrease because you're changing a 1 to a 0. So you should never do this. However, if at a different position, if at some position you have a 1 above and a 0 below, then you can say, hey, at this position, if I do a XOR, what happens? This gets converted to a 0, this gets converted to a 1. As a result of that, what happens? The lesser value becomes slightly greater, and the greater value becomes slightly lesser, and they come closer. So the leftmost bit already defines who is going to be the greatest. The leftmost bit, where we find this difference, we will keep them unchanged. That will decide, hey, this guy is going to lead. The other guy, we can make sure we are increasing wherever we can at the other bits. But leftmost bit or the leftmost different bit, the leftmost different bit, we are not going to fiddle with that. Okay, so let us see. Over here, we are not going to convert this to 1. So we will say, okay, XOR with 0 only. Don't change this. Here also XOR with 0 only. Over here, you have again a 0 1. So again no point changing it, so 0. Here you have a 1 0. So yes, there is some point changing it. If you XOR both of these with 1, what do you get? Basically your 9 XOR x will change to what? The last bit only gets toggled. So 1000, which is 8, and 6 XOR x becomes 6 XOR 1. So that is only the last bit gets toggled, which becomes 7. And now if we subtract it from 8, we get 1. So can you see that we have reduced it? We have reduced what we were getting earlier. If we XOR with 0, we got 3, but now we have reduced it to 1. So what did we do? We basically planned that, hey, let's identify the first point of difference. This is the first point of difference, so let it be as it is. This defines who is greater, who is lesser. Now from the next point, what we will do? We will basically try to increase the lesser one. And how can we increase the lesser? There is only one condition. What are the other conditions? If I have both are 0. Both are 0 means if I change both of them to 1, what happens? Nothing. 1 minus 1 is still 0. Nothing changes. If both are 1, then converting both of them to 0, what happens? Nothing changes. 0 minus 0 and 1 minus 1 is the same thing. So can you understand that if both are same, at a certain position, if both the numbers have the same bit, then XORing them with 1 doesn't make any difference, because the difference of those numbers at that position will remain the same. 1 minus 1 and 0 minus 0 are the same thing. So XORing with 1 does make no sense. But if they are in the form of 0 1 or 1 0, then the effect of XOR will be the 0 will become 1 and the 1 will become 0. And XOR is my favorite operation. XOR is my favorite operation. In my coding implementation, I'll show that even swapping I have done with XOR. So if you try to do a dry run on the way I've swapped, you'll actually find how XOR helps in doing swapping, and that's a very cool technique actually. Okay, so this is the property of XOR. Now, to add to the fun, what has been given is that your number x has to be less than equal to r. In this case, it is holding true over here. In other examples, it may not hold true. In other examples, it may not hold true. Now, this is important. Here, so if x was not equal, this condition was not there, it was easy. Find the first point of conflict, and after that, or first point of difference between the two numbers, decide who is going to remain greater. And from the next point, wherever you see that the bits are different, or even not different, wherever you see that after swapping, you can basically do something like this, that hey, try to swap at this bit, try to swap at that bit. So you can basically try to swap at every position. And if that gives you a better answer, then choose the swapping over there. Here you just need to do one step. So basically the logic is, the logic that we have discussed is, find the leftmost bit that is different in A and B, and let that be ith bit. So from the right we usually do the counting. So it's something like this. If it is 1 1 0 1 0 0 1, we count from the right. So it is 0 1 2 3 4 5 6. So if this bit is the bit that is different in both the numbers, we can say that I is equal to 6 is the bit we are starting from. Then we can basically say, hey, go from j, let's say, go from I minus 1 to 0. And if a minus b is lesser than a XOR the jth bit. How do we change the jth bit? How do we change the jth bit? By XORing with 2 to the power j. By XORing with 2 to the power j. Minus b XOR 2 to the power j And basically we can say if this condition holds, then we can say swap. Sorry, the opposite. So if I see that there is an improvement, over there. After zoring, the difference is lesser. Then definitely we can swap and sorry, we can zor. We can zor. If it is greater, then we can zor. So a equal to a zor 2 to the power j, b equals to b zor 2 to the power j. Right? Now the extra condition is given that hey, this you can't just zor with anything. The r is important. The r is important. So for that you can just maintain a variable whatever you're adding. So you can say that okay, for that extra condition you can say that okay, when you have that extra condition you can add that extra condition in this way, that and is my 2 to the power j less than equal to r, and you can keep on updating r. When you decide that okay, I will utilize this bit, then do subtract it. Here there are many things that are very interesting. We often neglect those things, but some of the very crucial things is that the jth bit is always, like this bit is always more crucial than all these bits taken together. 2 to the power 5 is greater than 2 to the power, I mean, the summation of the powers of 2 all over here. And that's why we say that, okay, if you're able to change that bit, change that bit. And then look at the other bits. That's the foundation of the greedy algorithm we are using. That is going from the left, right? So this is how we can process. I could have kept it equal also. But because of this R, I will say that, okay, swap only when you are facing an improvement, only when you are improving. If it is remaining the same after zoring, then no point zoring it. So yeah, this is the code. I did it, I think, in a slightly different way. But anyway, and this 2 to the power j, you can easily write it as 1 left shift j, something like this. 1 left shift j and 2 to the power j is the same thing. So since you're solving a bit manipulation problem, this is another instance of bit manipulation. Okay, so let us see. I think we can have one more example to establish that how this will happen. Let us see if we have some example over here. 92, 256, 23. So let us see. 92, 92 in binary gives me 1 0 1 1 1 0 0. So 92 is 1 0 1 1 1 0 0, right? Yeah. And I have 256. 256 means 1 followed by 16 zeros or something like that. 256, not 16, it will be, let's say 8, I think. 0 0 0 0 0, yeah, 8 zeros. So it's 2 to the power 8 actually. 256. So 0 0 0 0 0 0 0 0 1. These two. For this I have to decide, and the upper limit that is given is 23. 23, let us write that down. 23. 23 we can write it ourselves. It's 16 plus 7. So this is 16. This is supposed to be 16. Yeah. This should be 23. 16 is, yeah, 16 plus 7 is 20. Right. So now, over here, if I see, what is the first point of change or difference? This is the first point of difference. I will not change anything over here by principle. I'll keep that as it is. But now this becomes my greater number. This will remain my greater number. Now what happens? I come to this place. Both are zeros. So no need to touch. Come to the next position. 1 and 0. Definitely, I can change this to 0 and then this to 1. That will help me bring them closer. That will help me minimize the difference. But will this sum allow me? Will this power allow me? So this is 2 to the power 6 maybe, if I'm not wrong. 2 to the power 6, which is what? 64, is it? Yes, 64. So 64 is greater than 23, so definitely this is not allowed. Since it is less than r, since it is greater than r, this particular condition will fail and hence we cannot use it. So I'll say, hey, we can't do anything here. We can't do anything here. Next, over here, both are 0, so no question. Over here again, the top one is 1. So I will say, okay, I can do something here. This 1 is over there. So I will choose this. I will choose this 1 over here. So this one becomes a 0 and this one becomes a 1. I can just keep it highlighted. Let's keep it highlighted. Yeah. Now next point, 1 0. Over here also we can toggle it, but this 0 doesn't allow me. So I've reduced this r. 2 to the power j is now gone. Now 7 is the remaining value of r. So now I'll say, okay, this is I think this is, okay, not this one, the next one. This one is 8. So 8 is greater than 7. 8 is not less than equal to 7. So I can't have anything here. That's due to this particular condition. I can't switch that bit. Next one, again, 1 and the lower one is 0. So definitely I have interest in switching it. Below, okay, I'm sorry. So, the 256 one is the bigger one, so definitely there is no interest. We have no keenness to change this. So definitely this one also we will not change because this is, yeah, this one also we will not change because this one is this lesser one, the lesser one that is 92 has 1 over here. So no interest, there is no intent, no reason to change. That's it. We can slightly take a different example. Maybe make this as 256 plus 3, 259 if I take this. And basically it becomes 1, 1, something like that. And then let's switch this bit also. Then it will be a bit more fun. So we can say on switching this bit, we get 16. So this is 16, that is, the number is now 265, 275, 275. And the above number will be 92 minus 16, which is 76. This is 76 now. So now I'm solving with 76. Same way I started, and up to here I made no change. Up to here I made no change. Over here I can make a change, so I made my first change. Over here. I'm sorry. So I changed basically all of the bits to make the 256 change into 275 and the lower one 92 to 76. If we see the previous answer, we'll basically have the same thing. 92 to 256, nothing should change. So if I subtract it, we should get, yeah, 160. Is it 256 minus 92 is 164. Yes, 164. So nothing changes. But let us change it a bit. So I changed it to 275 and 76. Now this is the first thing we can change. The lesser one, the lesser number has lesser bit, 0. So I will change it. I have the quota to change it. So I will change it over here. Next one I cannot change. I am marking it with a different color because of this 0. I cannot change. And anyway, I will not choose to change that as well. But if I could change, I could not have changed because of this. If I would have liked to change, I could not change due to this. And so on. In the last two, I can see 275 is greater, so I can choose to actually have these swapped, so these two are going to get solved. The zeros and 1 get swapped. So yeah, this one basically becomes 0 1 0 1 1 1 1 1, and this one becomes 1 0 0 0 0 0 0 0 0. So this one gets converted to 256. This one gets converted to, let's see. So that is 1 1 1 1 1. 2 to the power 5 is 32, so that is 31. No, 31, that should be 63. 1 2 3 4 5. 2 to the power 4 plus 2 to the power 3 plus 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0 is 31. 31 plus 32 is not there, and 64 is there. So 64 plus 31 gives us 95. That's where we are, 95. 64 plus 31. 95. Yeah. So that's it. Now let us look at how this has been implemented. This is my own solution. If we go down, we can see that we can basically see that I first found out the first point of difference, where either x is 0, y greater than 0, or y is 0, x greater than 0. I'm basically fetching the ith bit, and this is the way I'm fetching, using bitwise AND. I'm fetching that ith bit, or you can say ith bit followed by that many zeros, and then I'm going from the next bit up to the end, and if I find that particular condition which I checked over there, y greater than 0, x equal to 0, I checked a different condition over there. I basically checked whether on swapping what happens, but basically here I'm checking the exact thing. Hey, is the greater one's bit 1 and the lesser one's bit 0? Then do the sorting. So this is where I'm doing the sorting. So I'm taking a as the bigger one. If a as a smaller one. If a was the bigger one, I just swapped it. There's some quick things to generalize things. A greater than a is always lesser than equal to b, that kind of thing. Finally, I'm printing the difference. Yeah. So before we finish, I want to show this, that this 1L is very important over here, so that when you do one left shift I, if you just do one left shift I, it will basically keep it in integer. It will not keep it in long. But 2 to the power something, basically if the number is going to 10 to the power 18, then you can't store that in int. So you can store that only in long. So I had to do this 1L. And only I think I had left doing this 1L in 2 lines, maybe these 2 lines. Other places I had done, due to which I was getting some wrong answer. And this was how I was basically debugging and figuring out what is the right answer. So these are some handy lines in Java through which you can find out what is the binary string, what is the binary form of a given integer number. You just print this, it will take the value and it will print the binary form. So this helps in the debugging. You don't have to convert what I just did on the screen now. You can just print it and you can use it for debugging. So that's it. Bit manipulation, as I mentioned, my all-time favorite topic. And if you can visualize the bits, it's just 1 or 2 steps away. You're just 1 or 2 steps away from the solution. And you just have to take those small steps, nimble steps, to get to the solution. That's it. Feel free to post any doubts in the comment section. Otherwise, do like, share, and subscribe if you find the video informative. I'll try to post videos for upcoming contests as well. If I miss some contest, if I miss some questions, if you have interest in discussing some other questions with me, connect me on LinkedIn or Codeforces, or even you can ask the same questions in the comment section. And we can have discussions. So if you have doubts regarding the problems I'm discussing over here, please do post your comments or questions. Take care, keep coding. Hope you enjoyed the session. See you all in the next videos. Thank you. Bye.